Hey folks, sorry I can't be with you today. Still feeling a little bit under the weather from last night, so um, notes today are going to be done kind of this way. So today we're going to start off with a concept called Lewis dot structures. So what you're going to see is this is for covalent molecules only. So even though I've got a bunch of different ones on here, we're really going to be more specifically talking about anything over on this side of the periodic table. Okay. All right. So these are the 8 different ways that we can draw, or different types of Lewis structures. So what I want you to notice here is when we have hydrogen, remember hydrogen has one valence electron. All right, so we just draw it at the top. Helium is going to have its 2 valence electrons, so we can draw it there. Boron will have its 3 valence electrons there. Carbon, notice how we're spacing these out. So the way that I guess I like to do this is I like to start with the symbol in the middle, right? And then I'll go 1, 2, 3, 4, 5. Let me redo that. I don't like that way. All right, here's how I like to do it. All right, a symbol, 1, 2, 3, 4, just like a clock, 5, 6, 7, and then 8. All right, so I'm going to work around the clock, and then what I'll do is I will start to just kind of double in when I need to. Okay, so if you notice carbon here, it's got 4 valence electrons. With its 4 valence electrons, they're all separate as much as they can. It would be like saying if you had 4 siblings and you had 4 bedrooms. Well, you're not going to double up, even though you could have so much space for activities. But I mean, there again, you're going to spread out as much as possible. 5 valence electrons here. Don't necessarily care where that double pair is, where the shared pair of electrons are going to be. That could be on the top, that could be on the side. You could draw it up here, you could draw it over here, you could draw it down there. Either one is fine. Okay. 6 valence electrons for oxygen's group, and then fluorine is going to have its 7 valence electrons. Notice you got one lone pair over here on the side. All right. Um, Neon, again, noble gases, going to have 8 valence electrons. So when we look at our dots here, our dots are going to represent the valence electrons. Now, the big thing when we talk valence electrons is that those are going to be useful for bonding. Whether that's ionic, whether that's covalent, it doesn't necessarily even really matter too much. All right. So just so you see it again here, all right, 1 valence electron with hydrogen over here. All right. Then we talk about 2, but we're not going to use 2. Boron's got the 3 valence. Carbon's got the 4, the 5, the 6, the 7. And then down here, we've got our 8 valence electrons. Hydrogen, or I'm sorry, helium up here is going to have its 2. All right. To be honest with you, again, we don't necessarily care about those. We don't care about those. We don't really even care about those. And even sometimes on this staircase here, sometimes we don't care about those either. Okay. All right. Every nonmetal really wants to have 8 valence electrons, right? So it wants to get over to this side as much as possible. That's where stability exists. All right. So the way that they can do that is they want to be able to, like hydrogen you see here, wants to get over and have 2. Well, that's because it wants to be like helium. Now, carbon, remember, carbon has an option. It can lose 4 or it can gain 4, right? In this case, we're not going to see that it wants to lose 4 as much. So for us here, what we're going to see is carbon is going to want to gain 1, 2, 3, 4. So connect like neon. Phosphorus, if we're looking at that one, 1, 2, 3 is what it's going to need. Selenium, if we're looking at its group, 1, 2, right? And iodine would be 1, is what it wants to add to it. So for it to get over there, that's how many we're talking about trying to have to share based on that. So again, here we would add 4 there. We need to share 3 there. We need to share 2 there. We need to add another 1 there. So that's how many we would have to add to get to that stability. Okay. So, because every nonmetal wants 8 valence electrons except for hydrogen, this is how it works in a compound of hydrogen fluoride. All right. So, when we look at hydrogen, hydrogen is going to have 1 dot on it. Fluorine we'll have 1, 2, 3, 4. Oh, let me do that the right way. 1, 2, 3, 4, 5, 6, 7. All right. So what you're seeing here is just the 1, the 2, the 3, the 4, the 5, the 6, and the 7. Okay. Now, with that in mind, what we end up seeing here is that our hydrogen needs one more. So it needs 1. The fluorine also needs just 1, which works out perfect because it has this spot over here as a, let me get a different color, this spot right there as a lone pair. Everything else in it, like here are 2, here are 2, and here are 2. So right now it's got 2 plus 2 plus 2 is 6. It's got 7, right? If it could get another electron right in this spot here, then all of a sudden now we got it full. All right. Well, hydrogen, it needs 1 as well, right? Then it's going to have its pair. The reason it needs 1 is because it's going to act like helium. All right. So what we end up seeing is that they will share this 7th one for fluorine and this first one for hydrogen. By doing that, what we see is we get 1, 2, 3, 4, 5, 6, 7, and 8 for our fluorine. All right. When we look at our hydrogen, we get 1 and 2, right? So now what we see is hydrogen is acting like helium, all right? And fluorine is acting like, what is it, neon, I believe, if I remember right, all right? Because it's got its 8 valence electrons. So they're both going to be stable, all right? So hydrogen only is going to need 1 bond. When it has 1 bond, that means that that one line will contain 2 electrons. That's a big deal for us, okay? That's a really, really big deal, is that anytime we get 1 line, that's going to be 2 electrons, all right? Now, when we draw these, the dots are going to again represent our number of valence electrons, okay? So helium and neon, so right here and right here, they don't need that because they don't want any extra electrons because they're already full and stable. So this one has its 8 valence electrons and it's stable. This one, remember, because row 1, when we look at helium, right, it's going to have its 2 electrons, which is the maximum number it can have. So it is also stable. All right. Boron's tricky because it's a metalloid. And so really, when we look at this one, boron is likely to do ionic only. All right. Meaning that it's only going to form through ionic bonds. All right. So once we see how these valence electrons set up and how we can draw them, then what we can do is start to show how they're actually going to create these different bonds for us, okay? So remember, 1 line is 2 electrons. That's a big one. I might write that one down. And actually, you know what I should do here, folks, right? I should change this to white so that you are going to write it down, all right? 1 line is 2 electrons, all right? So when we look at our hydrogen, there's going to be 2 electrons for it, right? So carbon, if it uses 4 bonds, so if it has 4 bonds, that's going to be 2 electrons, 4 electrons, 6 electrons, and 8 electrons, all right? Nitrogen, with its 3 bonds, right, there's going to be 2, 4, 6, and then obviously right there, those are 8, all right? This here is what we call a lone pair of electrons, okay? With oxygen, we got 1, 2, 3, 4, there's 5 and 6, there's 7 and 8, all right? 1, 2, 3, 4, 5, 6, and then there's our 7 and our 8, all right? So So in fluorine, you'll have 3 lone pairs. In oxygen, you'll have 2 lone pairs. In the nitrogen group, you'll have 1 lone pair. Now, if you notice, we always want to get all 4 of those sides filled up. So in like that fluorine, we want to get this top filled up, this bottom filled up, this and this with 2 if we can. If we can do that, then we're in a great place, all right? So when we look at writing the correct Lewis dot structures, the ones that are going to be correct for oxygen, remember, because it needs 6 valence electrons, should be that one, should be that one, not that one, not that one, not that one, not that one. And know that these 4 here still do have 6, but they have an empty space. I know what you're thinking, right? You're thinking, but there's so much room for activities on these sides here. No. That's not how they work. They want to spread out as far as they can. And these singles right here will move as far away from each other as they can. All right? With the nitrogen, we got 5 valence electrons. That works. That works. That one doesn't. That one doesn't. That one doesn't. And that one doesn't. Again, leaving an empty side like we see here, 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 and here, that's no. That's a no-no. All right, so when we have our rules, okay, rules for drawing those structures, we want to place the atom that can form the most bonds in the center. Can't have hydrogen. All right, so meaning if we can form 4 bonds, we want that one there. If it can form 3 bonds, we want it there. If it can form 2, we want it there. Give each atom its number of valence electrons. So what I would do is I would draw those in there first. Connect the atoms with at least 1 bond. Check that all have 8 valence electrons. It's called the octet rule. Except hydrogen needs 2. All right, don't forget that one. So if I'm looking at my CH4 here, right, C is going to have 1 dot, 2 dot, 3 dot, 4 dot. All right, my hydrogen, I'm going to have 1 of those dots, 2 of those dots, 3 of those dots, and another 1 right there. Okay, so there's my 4 hydrogens, there's my carbons. What I should see is, right, that one is going to pair with that one. That one looks like it's going to pair with that one. That one's going to pair with that one. And that one's going to pair with that one. All right. Now, when we draw these, we want to try and draw them out as far as we can. So you'll notice here, right, we're going to draw them so that they basically are a plus sign. So this thing will move up here. This one will move up there. That one will move right over there. And what we end up seeing is we get this with just lines and just letters. All right. So again, if we see this hydrogen has 2. Let me draw that with this. So this line here means that that's got 2, that's got 2, that's got 2, and that's got 2. All right. So our hydrogens are all good. Our carbon, 2, 4, 6, 8. It is also good there. All right. So that would be a perfect drawing for us. Okay. Let's practice these out. All right, so when we look at pH2F, all right, so P, 1, 2, 3, 4, 5. All right, I got 2 H's, 1 and 2, and I got an F, 1, 2, 3, 4, 5, 6, 7. All right, so in this case, this can form 3 bonds. All right, this can form 1 bond. And this can also form 1 bond, all right? Because of that, I'm going to pick phosphorus and put that in the middle. So P goes in the middle. 1, 2, 3, 4, 5. All right, are you starting to see? Right, lone pair on top, I'm not going to do anything with that, all right? So a hydrogen, I'm going to put that over here. I'm going to put the other hydrogen there, right? That's supposed to be big circles, sorry. And then I'll put my fluorine right over there. All right. So what that means is I can draw a bond here, draw a bond here, draw a bond here. All right. If I'm looking, that hydrogen, that has 2 right there. This one has 2 right there. All right. Let's see the fluorine. So it's got 2, 4, 6, and then there's 8 right there. All right, the phosphorus has got 2, 4, 6, 8 right there. So that would be a perfect drawing for us. All right, so let me clean it up and redraw it. 2 on H, 2 on H, 2 on F. All right, that's what that drawing would end up looking like. All right, SBRCl. So S is going to be 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. All right, Cl. 1, 2, 3, 4, 5, 6, 7. All right, so looks like S has 2 bonds, Br 1 bond, and Cl 1 bond. All right, that means Sr goes in the middle. All right, top, right, bottom, left. All right, so then notice my Br, right? It's got that single on that side. Well, I can move that single kind of anywhere I want to, that single electron. So what I'm going to do is I'm going to draw that Br here like this. I know it's got 3 lone pairs, and then I'm going to put that one there. Same thing with the Cl. I'm just going to twist it around a little bit, just kind of spin it so that it goes there. We then see, all right, that's going to form there. All right, let's check. 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8. All right, that one's all good. All right, let's redraw it so it looks cleaner. SR, 2 on the top, 2 on the side, down to a BR, or whoops, sorry, that's got to be a CL. So that's going to be a CL, 2 on the side, 2 on the left, 2 on the bottom, and then a BR over here. All right, that'll be our final drawing for that one. All right, C2 or C has 1, 2, 3, 4. H has 1. There's 2 of those though, and then F has 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. All right, so that's got 4 bonds, and both of these have spots for 1 bond. All right, that means the C goes in the middle, right? 1, 2, 3, 4. H's can go on a side. F, I'm going to put over here. Notice how I kind of move that around a little bit, those 7, so that the 1 was just kind of aligned nicely for me. All right, boom, a boom, a boom, and a boom. All right, let's see here. H has got 2, which it needs. 2 it needs. 2, 4, 6, 8. All right, that works. 2, 4, 6, 8. That works. Carbon. 2, 4, 6, 8. All right, that works. Here we go. So we get C with an H. Notice no dots on that one because it's got its 2 in the bonds. Same thing there. But both of these F's need it, so then they need their extra dots in order to show that they got full outer shells, full valence electrons. All right. Hey, hop out to homework. Check that out. Hopefully it makes sense. We'll talk more tomorrow and make sure that we're all good.